Welcome everyone, myself Shaheed-Ul will be strolling through the platform NEET major test powered by Platform Institute. Dear student, you don't know if you practice more than anybody, but you ensure yourself that you have practiced enough. You still wonder somebody somewhere is practicing more than you. You keep your practicing on and automatically accuracy catch you up. My dear students, let us see the first questions of this journey. Stay tuned with us. Do subscribe our channel. An iceberg is floating partially immersed in seawater. Relative immersion equal to, we can say, relative density. Let me explain what is relative immersion. Relative immersion is the volume of the body immersed by total volume, and relative density is the density of the body immersed or floating, partially immersed, by density of liquid in which the body floating, partially immersed. In this problem, the density of the iceberg, it is 0.92 by density of the seawater 1.03, and by calculation 92 103. So percentage immersion of the body is 92 by 103 into 100, and it is 89.32%. Okay. So volume of the body, above the level of sea water (100 minus 89.32%), and it is near about equal to 11%, and it is given in the problem option number 2. So correct option matches with the 2. Moving on the next problem of this session. Question number 2, a conductor with rectangular cross section has dimension A into 2A into 4 as shown in figure. Resistance across AB equal to R1, it is given in the problem. So it is rho, length is 4A by cross sectional area equal to A into 2A. This is A and the side, this side is 2A. So cross section of this is rho 2 by A, and we can write here 2 rho by A. Similarly, across CD equal to R2 given in the problem, it is rho, it is actually 2A and 4A into A. This side is A and this side is 4A. So cross sectional area becomes rho by 2a. And the third one, R3, it is actually REF rho between these two surfaces, this side and other side. The area of this side is, the length of this side is A, and this side is 2A and this side is 4A. So 2A into 4A, it is rho by 8A. So these are the resistance of the rectangular conductor across the different two opposite sides. And here R1 greater than R2 greater than R3. So in the descending order, correct option matches with 2. Next problem. Inside solid conductor, electrons move randomly and keep colliding with the fixed ions. If there are n electrons and velocity of it, the electron I1, 2, 3 up to n at a given time is V1, then we can say, since it is electrons move randomly, we can write here the average number of electrons is n, and the summation of velocity Vi, it is actually 0. So the mean velocity of electron randomly moving due to the thermal excitation without any external electric field. If we apply the electric field across a conductor, so electrons starts moving unidirectionally, and we can get the rate of flow of charge, and we will get the current. But when without any external electric field, electron moving in the thermal excitation, because of the thermal excitation randomly, so the average velocity of electron, it is always 0, and the right option here is 2. Let us see the next problem of this session. Ring is made of wire having resistance R naught is equal to 12 ohm, and as shown in figure, current enters into this and divides into two parts. Current in this division is I1 and current in the other part is I2. So current divides into two parts. Here the resistance R1 plus R2 is equal to 12 ohm, and it is given in the problem R0. And equivalent R1 R2 by R1 plus R2, it is in the problem equivalent of these two is equal to 8 by 3, and by solving we can get R1 equal to R2, that is 8 by 3 into 12, that is 32 ohm. Solving the two equation, R1 plus R2 is equal to 12 and R1 plus R1 into R2 is equal to 32, we can get R1 is equal to 4 ohm and R2 is equal to 8 ohm. And do you know, R1 by R2, it is actually L1 by L2, and by arithmetic R1 by R1 plus R2, it can be written as L1 by L1 plus L2. L1 plus L2 is the total length. So R1 is equal to R0 not necessary, it is at which current carrying conductor should be connected, so that the option are given L1 by L2, L1 by L2 is equal to 1/3, L1 by L2 is equal to 3 by 8, L1 by L2 is equal to half. So this part is not necessary. We can do this job here. The ratio of resistance equal to simple, it is L1 by L2. Right option here, the ratio of length of two parts is equal to, it is R1 by R2, direct proportion, it is 4 by 8, and the answer become half. Correct option here matches with 4. Let us move the next problem. Of a copper wire of cross-sectional area 2 mm square, resistivity 1.7 10 to the minus 8 ohm meter, carries a current of 1 ampere. The electric field in the copper wire. In the resistive circuit, potential difference given across the resistor of length L, it is actually V. Therefore, electric field E equal to, we can write the potential gradient. So this is the electric field applied across the conductor of length L, having the potential difference V. And we know J equal to sigma E, that is current density, is directly proportional to electric field applied across it, where sigma is the electric conductivity. And it is reciprocal of resistivity, electric resistivity. Electric field is equal to J by sigma, and finally it is rho. Reciprocal of conductivity is equal to resistivity, and J equal to I by A. Electric field, we can write it is rho into I by A. Cross-sectional area, it is given. Current through the conductor, it is 1 ampere, it's also given, and resistivity given 1.7 into 10 to the minus 8 ohm meter. So in this simple calculation, E equal to rho given, it is 1.7 into 10 to the power minus 8, and current in the circuit is 1 ampere, and cross sectional area 2 mm square. Therefore 2 into 10 to the power minus 6, and finally this calculation 17 by 2. I have done it 17 by 2, you know, all the option having the 8.5, 8.5, 8.5. Since the digit, that is 8.5, 8.5, 8.5, these are the common for all option. So just we have to check the power. It is actually minus 3. So electric field is volt per meter. So the right option in this problem matches with free. Let us see the next problem of this video session. The current I and voltage in the graph given metallic wire and two different temperature T1 and T2. Here the temperature of this is T1 and temperature of this is T2. It is V versus I graph. You know tan theta, that is slope of the graph. Tan theta represents here I by V. So it is reciprocal of resistance. Slope of this graph represents the conductance. Reciprocal of resistance, actually it is conductance. Conductance is C. I have written here C. Conductance. Since the voltage is taken along x-axis and current is taken along y-axis, and the slope of this graph is I by V, and tan theta is the slope of the graph, and which is 1 by R, and reciprocal of R is equal to conductance. R1 by R2, it is tan theta 2 by tan theta 1. Since theta 2 greater than theta 1, I should mention here the slope for this graph is theta 1 and slope of graph is theta 2. In this way we can write R1 greater than R2, and temperature variation, it is R naught, that a resistance of a conductor at 0 degree centigrade, into 1 plus alpha del T, that is the change in temperature. And you know, this is R naught, 1 plus, we can write here alpha T. Since R1 greater than R2, temperature for the resistance R1, temperature of the material wire T1, having T1 is greater than T2, because you know the resistance R1 is greater than R2. So we can write here temperature T1 greater than T2. Here the right option is 1. Next problem. An electric bulb marked 100 watt to 30 volt. If the supply voltage drops to 115 volt, what is the heat and light energy produced by the bulb in 20 minutes? You know, power consumption PC equal to supply voltage square by resistance R. That is the resistance of the coil, resistance of the coil. And you know, a rating given in this problem is equal to 100 watt to 30 volt. That is, this instrument at 230 volt can consume 100 watt power. And rating power, if I say it is P naught, this is rating voltage V square by resistance R. So consumption of power V square by R, I have done it is rating voltage by resistance into Vs by V. Vs is the supply voltage and V is the rating voltage whole square. So the power consumption is P naught into Vs by V whole square. So this is the formula for this type of problem. We can directly use this formula in such type of problem. PC equal to P naught supply voltage by rating voltage whole square. Rating power given, you know, it is 100 watt and supply voltage 115 volt. 115 volt by rating voltage is 230 whole square, and this is 25 watt. So this will be the power consumed by the electric bulb of rating 100 watt to 30 volt. But question is asked, light energy produced by the bulb in 20 minutes. Light energy, if we consider that the total electric power is converted into the light energy, don't take heat energy, light energy equal to, let us say it is E, and power consumption into time. Power consumption is 25 watt and time given in this problem is 20 minutes. 20 into 60 second. 12 into 25, that is 30,000 joule. Correct option matches with here. Option number 3. Next problem. Water is filled in a tank as shown in figure. There is a hole from where liquid emerges with a speed v. If air is blown over the tank, the speed v. We know a tank filled with water or filled with liquid coming out here, the velocity it is v. If the depth of the orifice it is y, so the velocity of liquid flow emerges out of the orifice, it is equal to root over 2gy by applying Bernoulli's theorem. Here one consideration, you know, pressure over the liquid surface, it is P naught, that is atmospheric pressure. It is ATM pressure. And pressure it is also P naught, that is pressure at a point on the orifice where just a liquid comes out of the orifice. It is here also the pressure is atmospheric pressure. But in the case When it is similarly liquid filled with the container, if the air is blown over the liquid surface, here the velocity is V prime, let us say, pressure, atmospheric pressure is P naught, but the pressure over the liquid surface, because you know, since the air is blowing over the liquid surface, the kinetic energy per unit volume or per unit mass, according to Bernoulli's theorem, total energy equal to constant. Since the kinetic energy of the air per unit volume increases, so the pressure decreases, pressure energy decreases. Pressure above the tank, since it is decreased due to the air flow over the liquid surface, the pressure on the liquid in the container decreases, and this velocity becomes less than V. So the speed will decrease. Next problem. Equivalent resistance of n resistance, each of same resistance was connected in series is R. Equivalent resistance R when connected in series, let us say the resistance of each conductor is molar. So the equivalent resistance, it is R equal to NR. If the same resistance are connected in parallel, in the case of parallel, the resistance become R by N. Okay. So replacing R, it is R by N, and R is the equivalent resistance when it is connected in series, it is N square. In the problem, the equivalent resistance when all the resistors connected in series is given R, so the Rp, that is equivalent resistance in parallel combination, is equal to Rs by N square. Correct option matches with 1. Simple question. Next problem of this session. 5 conductors are meeting at a point as shown in figure. We know, according to KCL, Kirchhoff's current law, the algebraic sum of current at any junction, it is equal to 0. So here 5 ampere current entering as per the diagram given. I have taken here entering the junction is plus entering the junction 4 ampere and leaving the junction minus 5 ampere and leaving the junction, it is minus 3A plus I, let us say current through, it is I equal to 0. Then 4 into 5, it is 9 minus 8 plus I equal to 0. I equal to, we can write here, minus 1 ampere. Minus means leaving the junction, plus means entering the junction. I have taken here plus when any current entering into the junction, and minus taken when any current leaving the junction. Since the answer is minus 1 ampere, we can say 1 ampere away from the X. X is the junction. So right option here is 2. Next problem. A vessel contains oil, density 0.8 gram per centimeter cube, over mercury 13.6 gram per centimeter cube. That is two type of liquid. In the lower, in some part of the container, the liquid is mercury, and some part of this container it is actually raw oil. A homogeneous sphere floats with half of its volume immersed in mercury and other half in oil. Density of the material of the sphere. Here the situation, half of the portion of sphere it is immersed in mercury and half of the portion of sphere it is immersed in the given liquid. You know, weight of the body acting downward it is mg and the total buoyancy it is b. Since this body is floating, completely immersed, it is floating but completely immersed, then we can say floating is, since the body is floating, then buoyancy equal to, we have to write, that is weight of the body. Now buoyancy, we have to find out the buoyancy due to the liquid. It has the two type of liquid, B1 plus B2 equal to mg. Half of the volume mg B1 plus B2. It is our problem. In this problem, the weight of the body mg is equal to B1 plus B2. B1 is the buoyancy due to one liquid and B2 is the buoyancy due to the other liquid. Okay. And let us say the total volume is V and density of body is rho into G. And we can write here it is V2, V by 2, half of the sphere immersed in mercury into G plus V by 2, other half of the volume immersed in a liquid of density rho naught. We can write it is density rho of the material of the sphere, rho Ag plus rho naught by 2. Density, you know, 13.6 and density of the oil it is 0.8 by 2. So we can write here it is 14.4 by 2 and finally the option becomes 7.2, answer becomes 7.2 gram per cc. So density of the material is 7.2 gram per cc. Here the right option Right option is 3. Next problem. The resistance of the 4 ohms PQR, it is PQRS by Wheaton bridge principle. By Wheaton bridge principle, it is clear from the problem is that P by Q is equal to R by S, and you can find the resistance across A and C and B. This is this point, let us say it is B. Let us say this point is B and this point is D. Since in this problem P by Q is equal to R by S, so no current pass through the galvanometer, because potential of the point B and the potential of point D are equal. So R equivalent, RAC equal to, current divides into two parts. It is I through PQ I1 and through RS is I2, and same current passing through P and Q and same current passing through R and S. No current pass through the galvanometer, that is through the branch B and D. So P and Q are in series combination, R and S are the series combination. PQ and RS having the two sides, current divides into two parts, so the equivalent resistance equal to 40 into 120 by 40 into 160. Sorry, 120. So 40 into 120 by 160, and this is 30 ohm. So the circuit current I equal to, we can write E by internal resistance plus external resistance. Since the current is passing through the cell and current is passing through the circuit is same, so we can say that the internal resistance and the external resistance are a series combination, so R plus R. Here the potential, that is EMF of the cell, is given 7 volt and resistance in turn. Next problem, it is 5 ohm and the external resistance is 30. We can say 7 by 35. So the circuit current is 0.2 ampere. So correct option here is 2. In a potentiometer, the null point is received at 7th wire. If we have to change the null point at 9th wire, what should we do? To shift the potential, to shift the balance point on higher length, potential gradient is to be decreased. We know in potentiometer wire, to balance the cell of EMF E, it is equal to V by L into L, where L is the length of null point, and it is K. If we want to increase the balance point, the potential gradient has to be decreased, and we know K equal to V by L, V by total length of potentiometer wire. Since K is decreased, if we want to decrease the potential gradient, then we have to decrease the potential difference across the potentiometer wire, and this can be done to connect a external resistance across the potentiometer wire or across the reference potential. We have to connect a resistance in series. So right option here is 2. Next problem. The figure below shows a 2.0 volt potentiometer used for the determination of internal resistance of 2.5 volt cell. The balance point of the cell in the open circuit is 75 centimeter. Here we have to find out the internal resistance of the cell. We know internal resistance R equal to capital R. This is L by L2 minus 1. Here L1 is the length of balance point. Without external resistance, and L2 is the length of null point with external resistance across cell. So the internal resistance R equal to external resistance across the cell, and the null point is 65 centimeter and external resistance is 10 ohm, and without external resistance the null point length is 75 centimeter. So this is 75 by 65 minus 1. This becomes 10 into 154, and finally it is 1.54 ohm. So the right option here is, for this question, is 3. Let us move on the next questions. So question number 15, the weight of a person is 60 kg. If he gets 10 to the power 5 calorie of heat through food and efficiency of his body is 28%, then up to how much height he can climb up? You know, the efficiency equal to, this is work done output by the heat energy input. We can write that is W is equal to eta Q, and it is 28%, and 10 to the power 5, so 28,000 into 4.2 into joule. So this amount of energy will be utilized to climb up. So W is equal to, it is 80,000 into 4.2. If we consider the height attained by this person is equal to h, we can write mgh is equal to 28,000 into 4.2. So height attained by this person is 28,000 into 4.2 by 60 kilo, and the value of G is 10. So by simple calculation you can calculate this numericals. It becomes near about 199 meters. So correct option matches with 2. Moving on the next problem on this video session, a stress of x kg weight meter square is applied to a wire whose Young modulus is y. The percentage increase in its length is, we know F equal to K into X, or K is a y into L, ay by L. It is actually force constant. It is known as force constant, and X is the expansion or elongation of the wire. So simple, F is equal to ay by L into X. So X by L equal to F by ay. And here it is F by A is the stress and it is y. Stress given in the problem is equal to x kg weight per meter square. So x into 9.8. The value of G here is taken 9.8 meter and it already been given in the problem. And Young modulus is y. Therefore, we can say the percentage expansion is equal to 9.8 into x into 100 by y, and by simple calculation we can say it is 980x by y. Correct option matches with 2. And the next problem, question number 17, aluminium and steel wire of same length and cross section are attached end to end. Y of steel is 20 by 7 times that of aluminium. So Young modulus of steel, it is 20 by 7 into Young modulus for aluminium. You know, two wire it is the string of aluminium and the another string connected to end, it is steel. If we put a force at the lower end of the steel, we have to find out the ratio of the increase in length of steel wire and aluminum, steel wire to aluminium wire. Here the same length and cross section. Again we can say F is equal to K into X. X is the expansion. And K equal to, you know, already we discussed force constant, it is A y by L into X. Here both the wire under the same stretching force. F is the force applied across at the lower end of this combination. So both the string under the same tension. So F same for both wire, and in the problem, you know, L and A, given in the problem, you know, it is same for the both wire. Therefore, we can say the x, that is expansion of the wire of individual wire, is inversely proportional to the Young modulus of the material. We have to find out the ratio in length of steel. It is the expansion for steel and expansion for aluminium. We can write here Young modulus of aluminium by Young modulus of steel. You know, and this value can be written, it is 7/20. So the ratio of increase in length of the steel wire to aluminium wire is 7/20. So right option here is 3. Next. Question number 18, Poisson's ratio is defined as, it is the problem asked on the simple questions asked on the definitions. Poisson ratio, you know, it is the ratio of the lateral strain by longitudinal strain. So right option here is 1. Next problem. Two wires having same length and material are stretched by same force and their diameter are in the ratio 1:3. The ratio of strain energy per unit volume. We know the energy density. We know energy density equal to half into stress into strain, and it is half stress is equal to F by A, and it is expansion by actual length. In this problem, you know, material Y, same for both. It is same for both. Force, it is also same for both the wire. Actual length, it is also same for both the wire. And you know, when stretched by same expansion, that is X is also same for the both wire. So these are the physical quantity which are all are same for these two wires under the same extension, under the same stretching force, and their actual length is also same, stretched by the same expansion. So therefore we can say the energy density is proportional to 1 by cross sectional area of the wire. We have to find out the ratio of the strain energy per unit volume. So U1 by U2, we can write here, it is A2 by A1, and it is R2 by R1 whole square. The ratio of the diameter is given, it is equal to 1:3. That is, we can say it is 3 by 1. And finally the answer becomes 9:1. Correct option matches with 2. Let us move for the next problem. Copper of fixed volume V is drawn wire of length L. When this wire is subject to constant force F, the extension produced in the wire is del L. Which of the following graph is a straight line? We know Young modulus. equal to F into L by A into X. In the problem, it is F, L, actual length of the wire, and A is the cross-sectional area of the wire, and X is the expansion given in the problem. It is actually del L, and V is the volume. Copper wire of fixed volume V is drawn into wire of length L. It is F into L square by, we can write A into L into del L. So F L square into V, that is the volume of the wire, it is del L. Because volume of the wire is given, and Y is the Young modulus of the material. We have to find out which one is straight line. You know, del L, we can write del L, that is expansion of the wire, is equal to F by Y into V into L square. So here we can say the expansion of the wire is directly proportional to L square. So del L is equal to, it is K L square. K is a constant. This is not force constant but constant, proportional constant. Del L is taken along Y axis and L square is taken along X axis. So this equation becomes straight line. So by comparing this, we can say the right option here, the change in length versus L square, is the straight line graph. We get the straight line graph del L versus L square. Next questions of this video session. Question number 21. By shaking through a straw, a student can reduce the pressure in his lungs is 750 mm of Hg. You know, normal pressure P atmospheric pressure, it is actually 76 centimeter of Hg. Pressure in the lungs of decreases to 75 centimeter. So pressure change is equal to 76 minus 75, that is 1 centimeter of Hg. Okay, so pressure change, due to this pressure change, he can drink the water from a glass up to a maximum depth. Because of this pressure change, height of the, if we think it is the height for the mercury column. H is the height for the mercury column, and rho is the density of mercury, and into it is G. You know, it is 1 centimeter of Hg, 1 centimeter, and it is 13.6 into G. If we convert it into the height of water into rho water into G, then the height of water becomes 13.6 centimeter, and the density of water, it is 1, and the value of G is Z. So height of water column, it is 13.6 centimeter. Right option here is 3. Next problem. Question number 22. A body floats in water with 1/3 of its volume above the surface of water. If it is placed in oil and it floats with half of its volume above the surface of oil, the specific gravity of the oil. A body floats in water with 1/3 of its volume. With 1/3 its volume above the surface, relative immersion, we can say again, relative immersion, I have told earlier, in the previous problem, relative immersion is equal to relative density. Relative immersion is equal to relative density. Simply we can say Ri equal to Rd for any floating body partly immersed, partially immersed, and relative immersion means the volume of the body immersed and by the total volume of the body, and relative density is equal to density of the body floating by density of liquid. It is given above the surface of water, 1/3 of its volume above the surface of water. So 2/3 of the volume immersed into water, 2/3 of the volume immersed into the waters, and it is rho B by rho water. From the first stanza of this problem, if it is placed in oil, it flows with half of its volume above the surface of oil. So by similar conception, half of the volume is immersed, and this is the density of the body by density of oil. So from these two equations, rho B by rho water, rho B by density of given liquid, rho L, it is equal to, we can write here 2/3 by half. Dividing these two equations, we can say the density of the oil, it is 4/3. So this is very simple questions, but you have to apply this formula, especially Ri equal to Rd. You can use this You can use this formula, that is relative immersion is equal to relative density, and relative immersion means the volume of the body immersed by the actual volume or total volume, and density of the body, that is with respect to the density of liquid. And we can get the two equation. Dividing these two equations, we can get the density of the oil. Next problem. The water equivalent of 10 gram of aluminium, it is specific heat, water equivalent, we can say W equal to mass into specific heat. So mass of the aluminium body, it is equal to 10 gram, and specific heat, it is 0.2 cal per gram per degree centigrade, and this becomes 0.2 cal per degree centigrade. We know it is equivalent to mass of water into specific heat of water we know specific heat of water is equal to 1. So the mass equivalent, water equivalent of the aluminium, it is actually 2 gram. So here the right option is 2. Next problem, number 24. A wooden ball of density sigma is immersed in water of density rho to a depth h below the surface of water and then released. In a container, liquid of density rho, and a body is immersed up to a depth h, and density of the body given in the problem, it is sigma. And we know buoyancy acts upward and weight of the body is downward. So here buoyancy is greater than mg. We can write body accelerate up, that is mass into acceleration, in equal to b minus mg, and we can write here mg b by mg minus 1, and acceleration upward we can write it is z, and buoyancy is the weight of the liquid displaced and mg is the weight of the body. So b by mg can be written as it is rho by sigma. So acceleration of the body is equal to z, rho by sigma minus 1. If we check the acceleration of the body and with the option, here sigma by rho, here rho minus 1 by sigma into h, sigma by rho minus 1 into h. Here one term is here, important term, the option number 3 having the term rho by sigma minus 1 into h. So probably by checking the acceleration only, we can say that the 3 is the answer. But if we want to solve the problem, we have to find out the velocity at the surface of water. We know the velocity of surface of water, v square equal to u square plus twice ah. So this is the velocity of the body at the surface of water, and it will flies off the surface and ascend up to a height, let us say it is 8 h, and gravitational retardation is z. So height attained in air, we can write directly h is equal to v square by 2g, and v square, you know, we already find out here, equal to twice a h by 2g, and finally it is a by g into h, and already we have found here a by g is equal to rho by sigma minus 1 into h. So right option again it is 3. Next problem. Question number 25. A water tank placed on the floor has two small holes pinched in the vertical wall, one above the base. The holes are 3.3 cm and 4.7 cm above the other. If the jets of water issuing out from the holes hit the floor at the same point of the floor, so one container contains some water, and the height of this, it is 3.3 centimeter, and height of the other orifice is 4.7 centimeter from the base. It is, let us say the orifice is O1 and the orifice is O2. One important concept, the ranges are equal for the liquid flux. This range will be equal for liquid, the ranges are equal of both the liquid flux coming out of the orifice O1 and O2, and the height of the orifice O2 is 3.3 centimeter and height of the orifice O1 is equal to 4.7 centimeter, and this range are equal for both the case. Important concept, ranges are equal for two orifices for liquid flux coming out of the orifices. When positions of these orifices are symmetrical about midpoint of liquid column, important concept about the midpoint of liquid column, ranges are equal for liquid flux coming out of the orifices when positions of these two orifices are symmetrical from the midpoint, that is the distance from the midpoint of the orifice O1 and the distance of the orifice O2 from the midpoint. These two distances are equal. If these two distances are equal, we can say the depth of the orifice O1 and the height of the orifice O2 are equal. So in this way you can write height of O1, height of O2 is equal to depth of O1, or the height of the height of the orifice O2 is 3.3 centimeter. So depth of the orifice O1 is 3.3 centimeter, and height of the orifice O1 is 4.7 centimeters. So total height of the liquid column. Height of the orifice O1 is 4.7 centimeter, and height of the orifice O2 is 3.3 centimeters. So depth of the orifice O1 is also 3.3 centimeters. So depth, it is the depth, 3.3 centimeter, height. So 4.7 plus 3.3 centimeter, and it is 8 centimeters. So this problem is asked is highly conceptual problem. You should have this concept that the ranges are equal when the positions of these two orifices are symmetrical about the midpoint. In this case, if the positions of the orifice if it is symmetrical about the midpoint, then we can say the height of the orifice O2 and the depth of the orifice O1 are equal. And height of the orifice is 4.7 centimeter. So therefore depth of the orifice is also 3.3 centimeter. So the answer is 8 centimeter. Here the right option is 3. And next problem of this journey, a heat, question number 26, a heat flux of 4000 joule per second is to be passed through a copper rod of length 10 centimeter, area cross section 100 centimeter square. Thermal conductivity of copper 400 watt meter per centigrade. The two ends of this rod must kept at the temperature difference of. So this is a rod, and this rod has kept with a temperature difference, let us say. So we know Q by T, it is the heat flux, that is the amount of heat flowing per second. Ka theta 2 minus theta 1 by length of the conductor. It is the L is the length, let us say. Simple questions, just we have to find out the temperature difference between the ends of the conductor. Q by T is the heat flux into L by A into K, and you know it is 4000 joule given in the problem, and length of the rod is 10 centimeter, that is 0.1 meter, cross section 100 centimeter square, that is 10 to the power minus 4, and the conductivity, it is 400, and 4 into 10 to the power 7 by 4 into 10 to the power 3, and finally it is 10 to the power 4 degrees centigrade. Temperature difference 10 to the power 4 degrees centigrade. sorry, 10 to the power 3, it is actually 10 to the power 5. Ten to the power 5, and finally the answer is finally the answer is 10 to the power 2. So 100 degree centigrade. Right option here is 3. Next problem. Question number 27. Coolness is felt while standing near a heavy ice block because energy radiated by ice is more. No heat energy is radiated by the ice. From body, more heat energy is radiated than that by ice. No heat is energy radiated by the body. So energy released and energy gain, heat energy gained by the body or heat energy released by the body. If the energy released by the body is more than the energy gained by the body, then we feel cold. That is, we feel coolness. Coolness is felt. So from body, more heat energy is radiated than that by ice. So option 3 is the correct option. Next problem. Question number 28. The coefficient of absorption of surface of a body is 0.35. When 100 calorie of heat is incident on the body, 40 calorie are reflected from its surface. Then the coefficient of transmission of the body. We know absorption plus reflection plus transmission. Fraction of energy absorption, fraction of energy reflected, and fraction of energy transmitted is equal to 1. That is unitary. The absorption in the problem is 0.35 and reflection out of 100 calorie, when the 100 calorie heat is incident on the body, 40 calories is reflected. So the reflected fractional part of reflection, fraction of the energy reflected is 0.4, and we have to find out T, that is the fraction of energy transmitted, coefficient, that is coefficient of transmission of the body, and here T is equal to 1 minus 0.75, and the answer is 0.25. This is the coefficient of transmission, that is the amount of energy transmitted with respect to the incident energy, that is 0.25. So we can write it is equal to 25 by 100. So 25%. We can say also the total heat energy incident on the body is 100 calories. So out of 100 calories, 25% of the energy transmitted through the body. So right option here is 1. Next problem. A black body radiates heat at temperature T1 and T2. Okay. This is not the part of problem. It has been written. Repetition. So a black body radiates heat at temperature T1 and T2. T2 greater than T1 corresponding the maximum energy. More at T1, more at T2 equal for T1 and T2 and independent of the temperature T1 and T2. Black body radiates heat at temperature T1 and T2 corresponding to maximum energy. We know Wien's law. Wavelength of maximum energy radiated, wavelength of maximum energy, wavelength of the radiation, wavelength of the radiation of maximum intensity. Lambda is the wavelength of radiation of maximum intensity is inversely proportional to the absolute temperature. And you know, energy radiation, it is h nu, that is frequency, and it is equal to AC by lambda. So frequency corresponds to maximum intensity, that is maximum energy, is directly proportional to the temperature, that is absolute temperature. Since in the case temperature T2 is greater than T1, so we can write here it is more at temperature T2. Three rods of same dimension have thermal conductivity 3K, 2K and K. They are arranged in zone. They are 100 degree, 50 degree centigrade and 0 degree centigrade. Temperature of their junction is. It is the junction, let us say the junction temperature is theta. Thermal current in this branch, it is I2. Thermal current in this branch, let us say it is I1. Thermal current in this branch, let us say it is I3. So according to KCL, we can write sum of the thermal current at any junction. I have taken here all the thermal current entering into the junctions. It is the consideration, first consideration, either or you have to take all the currents enter into the junctions, or you have to take leaving the junctions. But as per the Kirchhoff's current law, we can say the total algebraic sum, that is the algebraic sum of the total currents entering into the junction. I have taken all the current here and entering. So I1 plus I2 plus I3 is equal to 0. And you know, current 100 minus temperature of unknown junction, let us say it is X. So temperature difference by thermal resistance, it is the current, plus 50 minus X by thermal resistance, and 0 minus X by thermal resistance equal to 0. Three rods of the same dimension, that is length and cross section of the all rods are equal. You know, thermal conductivity, thermal resistance is equal to 1 by K L by A. L is the length and A is the cross section. L by A are common for all conductors. So this becomes K1 100 minus X. If we put the value of R1, L by A are common for all. So common term are omitted, already omitted. K1 100 minus X, and this is K2 50 minus X, and this is K3 0 minus X equal to 0. Okay. Value, it is given 3K, 100 minus X, 2K, thermal conductivity 50 minus X, and the conductivity for third one is equal to K, it is minus X equal to 0. And by simple calculation, it is 300 minus 3x, 100 minus 2x minus x equal to 0. 3x minus 2x minus is equal to 6x. 6x is equal to 400 and the x is equal to 400 by 6. I think it is 200 by 3 degrees centigrade. So correct option matches with 2. Let us move the next problem. Separation between the plates of parallel plate capacitor is D and the area of each plate is A. When a slab of material of dielectric constant K, thickness T, which is less than D, is introduced between the plates, in capacitance becomes. Okay. One important formula, let us say it is one capacitor and some of the portion it is dielectric is inserted of thickness D1 and some of the portion, let us say it is the dielectric of thickness D2. Dielectric constant for this part is K1 and dielectric for this part is, let us say, K2, and the plate area it is A. So plate area is common for both the dielectric, but their separation is different for different dielectric medium. For dielectric medium K1 the separation is D1, that for dielectric medium K2 the separation is D2. So we can say the equivalent dielectric, it is equivalent dielectric constant and D is the total separation. It is actually formula D1 by K1 and D2 by K2. This formula is very important. Here you have to keep that, or you should have the sincerity that you know it is the plate area, that is common plate area for the dielectric are same, but the separation for dielectric K1 D1 for dielectric K2 D2, when plate area same, separation is different for different dielectric medium, then you have to use this formula. Okay. Okay. Then it is the D is the separation, it is D by K. When a slab of material of dielectric constant K of thickness T, it is D1 by K1, let us say it is D2 by K2, and D1 is equal to D minus T, and it is the dielectric medium is air in this case, and similarly it is T by K, thickness of the dielectric medium is T and dielectric constant is equal to K. Here it is equivalent dielectric constant. So equivalent dielectric D by equivalent dielectric constant is equal to, it is D minus T, it is 1, and it is T by K. It can be written as D plus T it is better to arrange in this way. D minus T 1 minus 1 by K. So capacitance for this problem. Capacitance is equal to epsilon 0 A by D epsilon 0 K E A by D, write in this way, epsilon 0 A, and it is D by K E. We can write here epsilon 0 A is the common plate area, and D by K E already being deduced. It is D minus T 1 minus 1 by K. So the right option is 3. Next problem. In this journey, energy stored in capacitor dissipated during charging a capacitor bears the ratio. Energy stored in the capacitor and dissipated during the charging in the capacitor bears in the ratio. In a capacitor, let us say potential difference V and charge is supplied by the cell is Q, and here the charge stored is Q. So work done by cell W is equal to, we can write Q into V, and energy stored in capacitor. Energy stored in capacitor is equal to, you know, half into Q into V. Work done by the cell is equal to QV, but energy stored in the capacitor is equal to half into QV. So energy dissipated is equal to QV is the total work done by the cell, and energy stored is equal to half QV, and the energy dissipated in the conducting wire is equal to half QV. So obviously energy stored and energy dissipated in the conducting wire during the charging of a capacitor. So right option here is 1. Next problem. In the given circuit, a charge of 80 microcoulomb is given to the upper plate of the capacitor 4 microfarad. In the steady state, the charge on the upper plate of the 3 microfarad, this is 3 microfarad. You know, charge given, it is charge given Q, and capacitance C1, let us say capacitance C2, charge divides into 2 parts Q1 and Q2. Charge divides into 2 parts Q1 and Q2. Charge divides into 2 parts under the same potential. You know, charge is equal to Q is equal to CV, both the capacitor C1 and C2. So V is same for the both capacitor. V is same for both condenser. So charge divides into parts in direct ratio of capacitances. Okay. By simple calculation, we can write it is Q1 by Q2 is equal to C1 by C1 plus C2, and Q1 is equal to, let us say, total charge supplied is equal to Q into C1 by C1 plus C2, and similarly Q2 is equal to Q C2 by C1 plus C2. But here we have to find out the charge of the upper plate of 3 microfarad. Okay, so Q2 is equal to charge given to the 4 microfarad capacitor. It is 80 microcoulomb, and capacitance C2 is equal to, it is 3, and the total is 2 plus 5. 2 plus 3. So 80 into 3 by 5. So this is 48 microcoulomb. Right option here is 3. Okay. Next, question number 34. For condenser, each of capacity 4 microfarad are connected as shown in figure. Potential difference across this, the potential given here, it is the point P, and that this is the point Q. Let us say the point here taken is R and the point taken here is RS. So the capacitance is equal to across the RS, you know, it is 4 plus 4 equal to 8 microfarad, and equivalent capacitance across this, it is 1 by 4, 1 by 8 plus 1 by 4, and equivalent capacitance is equal to 8 by 5 microfarad. Okay. Energy stored, it is equal to half C V square. Simple question. Just you have to find out the equivalent capacitance of this combination, and the potential difference given across P and Q is equal to 15 volt, and the formula is equal to half C V square, you know, and it is half 8 by 5 into 10 to the power minus 6 into 15 square. 15 square is equal to 225, and it is 4 into 4, 5 into 10 to the power minus 6 joule, and 180 into 10 to the power minus 6 into 10 to the power 7 arc. All option given in the unit of energy, that is arc. So it is 1800 arcs. Correct option matches with 2. And next problem, 100 gram of water at 100 degrees centigrade and 100 gram of ice at 0 degrees centigrade mixed, then the final temperature of the mixture. Let us say you have to, if we consider the 100 gram water at 100 degrees centigrade, 100 gram water at 100 degrees centigrade, if the heat released by this water, if we consider the total heat is released by the 100 gram water at 100 degrees centigrade and becomes, it is converts into 100 gram water at 0 degrees centigrade. 0 degrees centigrade. So heat release in this process is equal to 100 into 100, it is into 1, that is 10 to the power 4 cal. So our heat bank, it is heat bank ten to the power 4 cal. Heat required, to melt 100 gram ice at 0 degree centigrade is equal to 80 into 100, so 8,000 cal. Here 80,000 calorie heat is required to melt the whole ice block. So from 10,000 cal, 80,000 calorie is already utilized to change the state of the ice. So ice converts into water at 0 degree centigrade. 80 cal is the latent heat of ice, So 2000 in our bank already 2000 calorie heat already in our hand, 2000 calorie heat, and this 2000 calorie heat can increase the temperature of 200 gram water, because water of 100 gram water 100 degree centigrade, it is already converts into 0 degree centigrade. So the 100 gram water at 0 degree centigrade and water at 0 degree centigrade, water of 100 gram at 0 degree centigrade when the ice melts into the water. So 200 gram water at 0 degree centigrade, and specific heat is 1, and temperature, let us say, will rise up to theta, and it starts from 0 degree centigrade. Okay, so 200 theta is equal to 2000, and theta is equal to 10 degrees centigrade. So 10 degrees centigrade is the right option here. 3 is the correct option. Next problem in our journey, 3 capacitors, each of 6 microfarad and are available. The minimum and maximum capacitance which may be obtained are minimum and maximum. Maximum, if this 3 capacitor is connected into parallel combination, so the maximum is equal to 6 plus 6 plus 6, it is 18 microfarad. It is simple. So option 3 and option 2 are not the right option here. And C minimum, when the capacitance are connected in series combination, so C minimum, it is 6 by 3 and it is 2 microfarad. So it's a very simple question. Right option is 4. Next problem. Assuming no heat loss, the heat released by the condensation of X gram of steam at 100 degrees centigrade can be used to convert Y gram of ice at 0 degrees centigrade into water at 100 degrees centigrade. Assuming no heat losses, heat released by the condensation of X gram steam at 100 degree can be used to convert Y gram of ice at 0 degree centigrade into at 100 degree into water at 100 degree centigrade, the ratio of X and Y. Heat released by steam. It is released by steam, 540 cal per gram is the latent heat It is given in the problem, it is X cal, and heat required for this transformation is equal to y into 80 plus y into 100 into 1. So 540, therefore according to questions 540x into 180y, and we can say x by y is equal to 1 by 3. Right option is 3. Next problem. Question number 38. Two identical metal plates are given positive charge Q1 and Q2. You know, condenser, the charge given in the plate Q1 and the charge given in the plate Q2. We know the capacity is independent of charge. It is epsilon 0 A by D. D is the separation and A is the common plate area. You know, both the plate given the charge Q1 and Q2, electric field due to the charge Q1 is E1, and electric field due to the charge given in the plate 2 is E2, and electric field, the resultant electric field, let us say it is E. So electric field inside this condenser, it is sigma by 2 sigma 1 by 2 epsilon 0 minus sigma 2 by 2 epsilon 0. It is Q 1 by 2 epsilon 0 into A Q1 minus Q2. Q1 by A is the surface charge density and Q2 by A is the surface charge density of the plate 2. And the potential difference. Potential difference V is equal to, you know, it is E into D. Therefore, we can write here D by 2 epsilon 0 A Q1 minus Q2. Capacitance epsilon 0 A by D, and replacing here we can say the potential difference V is equal to Q1 minus Q2 by 2C. It is the potential difference between these two plates. And the correct option matches with 4. Next problem. Question number 39. Two plate parallel capacitors are similar in size, but one has glass dielectric and another ebonite. The capacitor with glass dielectric charged, but when the charge is shared between the two capacitors, the potential drops to 0.6 of 6 volt, 0.6 volt of its original value. So let us say we know the common potential Vc equal to C1 V1 plus C2 V2 by C1 plus C2. And we know the common potential, because of the sharing of charges between the two condensers, one condenser is charged and other condenser is uncharged. Here the capacitor with glass dielectric is charged. So capacitor with the glass is charged and capacitor with the ebonite is uncharged. So potential becomes 0.6 and it is C1 it is kg into C. Let us say the potential across the condenser of the glass G, when it is charged it is V, and the dielectric constant Kb for ebonite, and it is capacitance of this is C, and potential before sharing is 0. After sharing the potential is 0.6 V, and the capacitance here Kg C plus capacitance of ebonite, let us say Kb into C. So simply it is 0.6 Kg plus Kg by Kg plus Kb. Here we have to find out the original value. The SiC of ebonite is to that of glass each. So we have to find out here the dielectric constant for glass Kg, and it is Kg plus 2. We can write here it is 3 by 5, and 3 Kg plus 6 equal to 5 Kg. So 2K suffix G equal to 6. We can write here Kg. The dielectric constant of glass is 3. Correct option matches with 3. Next problem of this journey, energy per unit volume for a capacitor having area A and separation D kept at potential difference V is given by. We know energy density means energy per unit volume. It is half into epsilon 0 square, and E is the electric field. Across electric fields between two plates of condenser. Okay. If the electric field between two condenser having charge, negative charge, positive charge, and electric field is E, and let us say potential difference is V, and their separation is D. So electric field can be written as the potential gradient, that is potential drop per unit length or per unit separation. So energy, it is very simple question, direct question asked, just formula based questions. Half epsilon 0 and electric field is equal to V by D whole square, and the right option here is 1. Next question of the video session. The condenser one of capacity C and the other capacity C by 2 are connected to a V volt battery as shown. The work done by cell in charging condenser each. First of all, we have to find out the equivalent capacitance. C is equal to C plus C by 2, and it is 3 by 2 into C, and the charge stored in the condenser Q is equal to, we can write it is C E into V, and it is 3 by 2 CV. Work done by the cell. Work done by the cell. W is equal to charge supplied by the cell is Q and potential difference is V, So Q is equal to 3 by 2 CV into V, and finally the answer becomes 3 by 2 CV square. In this type of problem, this is simple problem, but sometimes student may find the wrong answer, half CV square, so the answer may be the 1, but here the question is actually work done by the cell in charging the condenser. The right option here is 3. Next problem. If a dielectric plate of thickness T is placed between the plates of a plate parallel capacitor of plate distance D, the capacitor becomes half of the original value. So capacitance, you know, epsilon 0 A by D, and capacitance, new capacitance, it becomes C by 2 due to insertion of dielectric medium. Epsilon 0 A, it is D minus T1 minus 1 by K. It is the capacitance, new capacitance, that becomes, this becomes half, and you know, the due to insertion of dielectric, it is due to insertion of dielectric constant, dielectric medium of thickness T. So equating these two, we can write 2D is equal to D minus T1 minus 1 by K, and it is D by T is equal to minus 1 plus 1 by K. 1 by K equal to, we can write 1 plus D by T, and it is T plus D by T, and finally the dielectric constants of the dielectric constant of the plate will be, it is equal to T by T plus D, and the right option here is 3. Next problem. The 3 capacitors each of capacity 1 microfarad are connected in such a way that the resultant capacity is 1.5. Then error and trial method, all 3 are connected in series. If all 3 are connected in series, we can write here, you know, all 3 connected in series, then the capacitance become 1 by 3. So this is not the right option. All 3 connected in parallel. Here in the case, the capacitance becomes 3 microfarad. So 3 is also not the right. 2 is also is not the right option here. 2 of them are in parallel. 2 of them in parallel. In the case of parallel, it is 1 plus 1, that is 2 microfarad, and connected in series to the third. So equivalent equal to half into 2 of them are in parallel and connected in series to the third. So it is 2 into 1 by 2 plus 1. This becomes 2 by 3. The result becomes 2 by 3. 2 of them in series, and so this is also 3 is also not the right option. 2 of them are in series. It is for the 3, 4 in the, for the option 4, 2 of them in series. 2 of them in series. So 1 into 1 plus 1 plus 1. This is half microfarad, and with third one parallel. Therefore, we can say 1 plus half. So this is 3 by 2 microfarad. Okay, so this is, you have to proceed all the, you have to check all the option, trial and error method. The final answer becomes, it is 4. Next problem. In Newton's law of cooling, rate of cooling d theta by dt is equal to minus k theta minus theta naught. It is the Newton equation of cooling. But you know, neat heat radiated, it is equal to Q1 minus Q2 by the body as per the Stefan-Boltzmann law. It is sigma EA T to the power 4 minus T to the power 4. So this is the neat heat radiated by a body. Here A is the surface area. It is surface area of the body, and it is the rate of heat radiation. Okay, and we can say therefore M is d del theta by del t. Del theta by del t is equal to sigma E T to the power 4 minus T naught to the power 4. Here del theta, that is rate of cooling, del theta by del T is equal to, finally sigma is the Boltzmann constant, E is the emissivity of the body, E is the emissivity of the body, and here E into E into EA by MS T to the power 4 minus T naught to the power 4. If T is not sufficiently large, if the temperature of body slightly greater than T naught, that is temperature of surroundings, then we can say del theta by del T is equal to sigma EA by MS. It is 4 T naught Q T minus T naught. Okay. So the rate of change of cooling is equal to, we can write is equal to K T minus T naught, and the value of K becomes 4 sigma EA T naught to the power 3, and it is the value T naught to the power 3 by MS. So K, in this problem the constant K is proportional to surface area of the body and inversely proportional to the mass of the body and inversely proportional to the specific heat of the body. Okay, so this is the based on the Newton cooling law, but K is a proportional constant which depends on the 4 sigma E. A is the surface area, T naught is the temperature of the surroundings, and M is the mass of the body, S is the specific heat of the body. So K is directly proportional to the surface area. Next problem. How much work is required to carry a 6 microcoulomb from the negative to positive terminal of potential difference 9-volt battery? It is simple question. Work done, you know, it is equal to Q V2 minus V1, that is charge into potential difference. charge into potential difference, and the charge, you know, 6 microcoulomb from the negative to positive terminal of 9-volt battery. Okay, so the charge is 6 into 10 to the power minus 6 and the potential difference is 9, and this is 54 into 10 to the power 6 joule. And the right option here, the correct option matches with 3. And in this way, we have discussed 1 to 45 questions of PMT03, which already conducted in the platform major test series. I think, we hope that you are all benefited from this discussion and you can act accordingly in your examination hall. That's all. Best of luck to all of you.